So welcome back class for the lecture on applied computer vision. In lecture number 2 we saw the different types of noises and we saw how to filter those noises out of the images. So we uh, we saw two different types of filters, the averaging filter and the Gaussian filter, and we saw how those filters they work. We in detail we observed the concept of correlation, how it works on the images. So here we will continue the discussion and we will see two concepts, correlation and convolution, with respect to images. These concepts they come from the signal processing domain, so they are the same concepts over there but they will be used differently over here. So before we go further to discuss these things, first of all we will discuss the concept of linearity, because the linearity or linear property, it is the property of systems or functions that we will be using in the future in the next chapter to see different concepts in computer vision like edge detection. So linearity of a function or a system, it means that an operator or a function, it is linear if it satisfies these two properties, additivity and scaling. So scaling and additivity. So additivity means that if, let's say, so these properties they are common for systems. So let's say you have a system, any signal processing system or any circuit. So let's say this is your circuit. When you provide this system an input x1, so I will write over here the function. So this is your function h. When you provide input x, it gives you some output y. Okay, so I don't define these values particularly, just a rough example. So when you give the input x1 some particular value like 5 or 4, it will give you some particular output value y1. Okay, so you can describe x1 as a one single value, or it can be a set of values like a function, like a sine wave. So sine wave is a set of values that are changing over the period of time. So the output will be correspondingly changing. If you change the input x to x2, the output will also change to y2. Now the linearity property, it says that for this same system, if you give it a value x1 plus x2, the system will be linear if the output is also the sum of these two outputs, y1 plus y2. So why it is important? The linear systems, they are more predictable. You can easily judge the output. So if you have an input x1 plus x2, because it is based on the previous inputs, you can predict the output accurately, correctly, that the output will be y1 plus y2. That's what we call it as linear. Okay, so this is the first property for linearity. Another property that is required for linearity is that the system, it should be able to scale the values. For example, if the input of the system is multiplied by 5, the same 5 should be multiplied with the output y. Nothing else should change. Okay, so there should be no effect on this constant 5. It is simply multiplied with the output. That is called as scaling. So let's say if you have an input like this, okay, and for some reason your system maybe makes this sine wave. Let's say you have a system that makes your sine wave, converts it into cosine wave. Okay, so this is sine of x, so maybe you take a derivative, so your function is derivative, the output is cosine of x. Okay, now if you say that your system's input is changing, which color should I choose? This one. So let's say you say that my input is increased, doubled. So this is 2x. The output will also change, 2y. Same magnitude. That is the meaning of scaling. Whatever factor you increase on the input side, same factor should be increased on the output. So these are the two properties that make any function or any circuit as a linear function or a linear circuit. Why it is important? It is important because if you remember, we studied earlier in the last chapter, filtering process, it is made up of two things, sum and multiply. And these sum and multiply, they are nothing but these are the basis. They are same things that are used over here for linearity. That's why the filtering process overall is linear process. So linear systems, why they are important? You can search on the internet a lot of examples. Linear systems, their behavior is predictable, easy to find out, and they have much more uses. So in the next chapter we will see. Here is one quiz, a small example you can expect in the exam. So you are given a set of different functions over here. What do you think, which one of them are linear? So out of these functions, sum is linear because we saw just previously adding or additivity is one of the properties of linearity, so it's linear. Another property that is based on sum is the averaging. What is averaging? Let's say if you have two inputs A and B. Okay, so averaging means for inputs A and B, the averaging means that you take the sum. Averaging is this thing, averaging, and then you multiply it with 1 by 2 where you have only two inputs. So basically averaging is made up of two operations, multiply and add. That's why it is also linear. Whereas these two are not linear. Max is not linear and square root is also not linear. Why it is not linear? You can try it. So for example, in the exam you can be given any other function. You have to find it out yourself. You can just try. So let's say I give you value, for example, I give you a function h of x equal to square root of x. Is it a linear or not? That's the question in the exam. So you can just try to get any value. So you can take some other value, but I will take some values that are already squares, so it's easy to find out. So let's say if the x value is 16, the output I will get is 4. If the x value is 25, output will be 5. Okay. Now the question is 16, and if the input is 9, the output will be 3. Okay. Now if I ask you 16 plus 9, it is how much? 25. Okay. So 16 plus 9, is it same as 4 plus 5? Okay, remember the rule, x1 plus x2 should give you the same y1 plus y2 if the system is linear. But here it is not same because it is giving you 9, whereas the answer should be 5. Sorry, 4 plus 3. So 16, the answer is under root is 4. 9, the under root is 3. So 4 plus 3 is 7. 7 is not correct answer because the answer should be the square root of 25 is 5, which is not same. So 7 is not equal to 5, so square root is not linear. Same is the case, you can find out max is not linear because max is a function that depends on the input values. So for example, max of two inputs 3 and 5, it is 5. But next time if you change the input, max will change. Max of 12 and 5 is, this time it is 12. So there is no particular formula that you can write for the max function. No mathematical formula for this. So this is the reason. So the overall correct answer is that these two are non-linear. B and D are non-linear. Clear? I hope it's clear, or you can search the internet for these things. This is the concept that you should have studied in your signal processing courses. Another concept that is related to this that also comes from the signal processing domain is called the impulse signals. What is impulse signal? Impulse signal is a signal that has almost zero duration. The duration is so small that it's almost zero. And its area is equal to 1. Area means length multiplied by width. So if the width is almost zero, so time taken is almost zero, then its height will be very, very large. Okay. Theoretically, it should be infinite. That's why the area will be 1. What is the importance of impulse? Impulse is a signal. So here I will show you, then I come back. Impulse is a very important signal used in signal processing domain, where it can help us to find out the behavior of any circuit. Let's say you buy, or an engineer, he buys a board or a chip from the market. Now they want to find out what is this board. So such a board is normally called as black box, because you don't know what is inside this board. You don't have any idea what is inside this board. That's why it's black inside. So you don't know how it works. For that purpose, that signal processing engineer, what they will do is that they give an input to this board or this chip or circuit. They give it an impulse signal as input. So impulse is like a unit signal. So when they give it an input, a unit input or impulse, they will get some output. So what does it mean? The output that you got over here, that is like the response of the system. That is the response or reply of the system. Now the advantage is that impulse is like a unit. Whenever now you give some other input, for example, you give us a value 5, it is just like you multiply 5 with impulse. The output will be the multiplication of that response, 5 times that response. Okay, so over here, for example, so I give you an example. Let's say you provide the impulse and you find out that when you give impulse, which is a unit, impulse is normally called as unit signal because its area is 1. So you see that your output is 5. Okay, so next time whenever you give any value, it is just multiplying it with 5. That's the response. So now you know what is the response of your system. Okay, let's say you have a signal X, and when you provide the impulse, you see that the output is -1. In that case, you know that now this signal is basically inverting the input. So if the input is sine wave, the output will be inverse of this, which is cos wave. So it is going positive. Here the output will be going negative. Clear? So this is how it works. So it starts with like this. Impulse is used to find out the behavior of the system. That is the reason we use impulse in the signal processing. So overall, such a response of the system is also called as impulse response, because it is the response of the system that you find with the help of an impulse signal. So one property you should remember, that impulse response can be applied to such signals, such systems that are linear. If the system is not linear, you can't apply impulse on that system. That is why we studied linear before. Okay, so here if you see, impulse is a very easy signal to understand. It has just a value of 1. its area is 1. Okay, practically in theory its time taken will be almost 0, but its amplitude will be very high, just near. Theoretically it should be infinite, but in practice we have a signal that has some time period as small as possible, but correspondingly the height should be that much that overall the area of the signal is 1. Area should be 1. So either the signal has a little bit of width, then the height will be less, or if the width is more smaller, so here if you see the width is smaller, then the height will be more higher. Okay, so in the continuous domain or continuous signals, impulse is basically an ideal function that is very narrow and very tall. Overall it should have a unit area. Unit area means the area is 1. And this is why we use it. Impulse is used to find the behavior of an unknown system. So that's why we use it. So why we studied this impulse? We studied this impulse because we want to use same thing in our image processing. Remember in chapter 2 we discussed that we will study some concepts from signal processing, and then we will try to use them over here in computer vision or image processing. So we studied impulse. Now we want to see, if you remember, what is this? This is our mask. Okay, so this is my mask. Now remember, the purpose of impulse is to find out what the system does. What is this H? Find out H. What is the response? What is the operation that is done by this black box? So here we want to use the impulse to find out how this correlation works. What is it that correlation do to our image? Okay, so remember in the last chapter you studied correlation. You know how to use it, but we still don't know what exactly it is doing, how it is exactly working. It is using multiplication and addition, but how it is doing it means what is the overall effect, that we will discuss over here. For this purpose we try to study the impulse. So impulse in the digital domain. So remember, in theory, in the impulse signal is like this, very almost close to 0 time period, and the height or amplitude is reaching infinity. But practically in the digital domain, impulse is a square wave like this, very short duration square wave like this. Similarly, impulse in the image processing domain is basically an image, a big image, maybe any size image, which has all the values that are 0, but there is only one value which is in the center, and it is 1. This is our impulse. Now I apply this impulse on my mask, okay, and I try to see what will happen to the mask. So what the mask is doing to the impulse, okay, whatever is done, that will be the response of this correlation. So remember, this operation over here that we perform is correlation. Okay, so that is what we want to study over here. So what is the result of filtering the impulse signal? That's what we want to see over here. So let's see one by one. All the other values, remember, the ones that are up over here, they will be 0. So here all these values above, they will be 0, all of them. Okay, so we don't care about them. The value that you see over here, so it will be 0. So the window size is, remember, 3 by 3. So these are 9 values. I will add them up. So there will be 9 values. And remember, we want to find out the value for this cell. So there are 9 values. Out of them there is only one value which is 1. So each value will be multiplied with the corresponding mask. So 0 will be multiplied with A, another 0 will be multiplied with B, and another 0 with C. Finally, only one value will get the will be reflected in the output, that is 1 multiplied by f. So the output will be f. Okay, so remember, I don't show over here 1 by 9 because 1 by 9 is already over here included in the mask. So remember, if you have a box filter with 1 by 9, it is like this: 0.11, 0.11, all of them. Okay, so that is the result I am showing over here. A over here is 0.11. If it's a box filter, it will be 0.11, all of them. Okay, so I want to see the result. We write over here A, B, C, D. Why we don't write same value? Because we want to see what will be the result in the output. If I had written all the values same, then the output should not be clear. I choose this mask, which is not a real mask, because I want to see what is the effect of this mask on the output. So you will see it clearly. Okay, so for the first value, the output is f. Now I move the window. This time the 1 will be multiplied with e, and the result will come over here. So it will become e. Next time I move the window. This time d will be multiplied, and I will see the d. So you see over here, the filter has the values d, e, f. Over there the values are f, e, and d. So it's like flipped. And you continue like this, and you will see an interesting pattern. The filter, the mask was A, B, C, D, E, F, and it becomes like this. So it started from the top, here it starts from the bottom. So what has happened? Basically, in the correlation operation, what we have done is that we have moved this mask 180 degrees. Okay, or you can say that I flip it to the right and then I flip it to the bottom. 2 times flipping. So it gives you same thing. A, B, C. If you rotate it 180 degrees, A will come over here. So this has happened. So basically the correlation operation, what it does is that it will apply the filtering on the image, but first of all it will make the mask rotate by 180 degrees. That's what is happening. So that is the result of the operation. That was the purpose of introducing the impulse signal. So impulse has given us the exact behavior of the mask, how it will occur. So this is it. Now one more question that comes over here, that suppose your kernel and mask are same thing. The size of the kernel is 3 by m, let's say 3 by 3, and the image is bigger, let's say image is 10 by 10. How many times you will do this multiplication that you see over here? Okay, so remember, you multiply A with 0, then B with 0, then C with 0. All of them you are multiplying, only the E multiplies with 1. So how many multiplications you will do in total? So it depends on the size of the image. So image is 10 by 10. And the mask is 3 by 3. So overall, how many multiplications you will do is that you will take this 3 by 3 mask and you will move it on the whole image one by one. And practically how many multiplications you will do is, you will do 10 multiplied by 10 multiplied by 3 multiplied by 3. You will do 900 multiplications. So the correct answer in this case is that for your m by m size, so m by m can be any size, m by m filter and n by n image, overall there will be m square n square multiplications that will occur. Clear? So This is the typical example. So remember, we don't discuss formula, but this is the symbol you should remember. This is the symbol of correlation. So H is our filter, F is the image. The output that comes is, let's say, called as G. There is another operation. So the operation that is used over here, it is called correlation or cross correlation. There is another operation that comes from the signal processing domain. I don't know if you remember, but it's very common. It is a must operation that is taught in the signal processing courses, called as convolution. So convolution is represented by this star symbol. So it is represented by star. What is the difference between correlation and convolution? In the case of convolution, when you have an image, I think it comes somewhere next. Yeah, this one. So if you have a mask, so this is your mask or kernel, and this is your image. In the case of convolution, the multiplication that occurs, it is direct. You don't rotate the filter. Okay, the mask is not rotated. Whereas if you are going to perform the correlation, in that case the result is same, but the image, the mask, you will rotate it. Let me explain it. So here is your image, and so here is your image F. When you do the convolution with H, it will be same as if you do the image and correlation, but if the filter or any one of those images is rotated by 180 degrees. So H over here I represent as H dash. So H dash is 180 degrees rotated H. What I want to say is that, remember, if this is the convolution operation taking place, you will directly do the averaging operation that you learned in chapter number 2. But if it is correlation, the only difference between correlation and convolution is that in the case of correlation, first you will flip it 180 degrees and then you apply the convolution. That is the only difference between convolution and correlation. Clear? No other difference other than that. So when you convolve a filter with an impulse image, we get the filter back as a result. So in the case of image, if you go back, let's say instead of correlation, here you have a convolution signal. Then what should be the answer? Now it will be more clear if I give example. Now in this case, what should be the answer? Let's go back. I will delete this. Yeah, this one. So let me draw it in another color. So let me choose blue. So I change this. I put over here correlation, convolution. Now I have an impulse signal, okay, and I want to find out what will be the convolution of impulse with the output over here, with the mask over here. The mask over here will give me the, when it is convolved with the impulse, it will give me the answer straight away. Simple averaging. Simply it will multiply the values, because most of the values are 0, so it will give me the straight answer. So now you see the result. What is the difference? In the case of convolution, the result is simple straight away multiplication. A, B, C, D, E, F, G, H, I, simple straight away multiplied. Whereas if it is correlation, the output will be this thing, inverted, 180 degrees inverted output. So convolution and correlation, they are same, but 180 degrees rotated. So I can write over here the convolution operation is same as correlation operation, which is rotated by 180 degrees. The result of correlation rotated by 180 degrees will give you the original answer of convolution. Clear? I hope it's clear now. I gave you examples. So this is it. So this is the quiz. The quiz says that convolution will give you the original impulse image. Okay. So when you convolve a filter with an impulse image, you will get the filter. So remember, the impulse image is nothing. It is just only one dot, one single value 1 in the center. All other values are 0. So when you convolve the filter with the impulse, the output will be the filter. Okay. So if you say like this, filter, you do convolution, and with the mask, the result will be simple image F. Sorry, not F. It will be your H. So H is your mask. So the impulse signal that you provide, impulse has nothing. So output will be simple H. Same. So if you convolve, now the question is this: if you convolve an image with an impulse, what you will get? Okay. So that's the question. If you convolve an image with an impulse, what you will get? So on one side you have an image. So image is like this, some big image, and you convolve it with an impulse. So impulse is a function that has only one value in the center and all other values are 0. Okay. So when you do this, what will happen? That's the question. We will do this in the lab work, so don't worry if it's not clear here. But when you are taking an impulse, you multiply or convolve it. Convolve is just like a simple straightaway multiplication. The answer will be the original image, no change. Clear? Why it happens like this, I will discuss in the lab work in more detail. So these are some of the properties we study over here of the kernels, of the operators, correlation and convolution, and how they behave with respect to the mask. Some more properties we will study for convolution. So remember that all the operations we study over here, they are linear. Either it's convolution or correlation, they are both linear. There are some more properties for convolution that they are shift invariant. What does shift invariant means? Shift invariant means that the operator, it behaves the same for the given input anywhere in the function. So let's say this is your image I, and you want to apply or correlation or convolution the mask. Okay. So if there are some values over here and that same image value repeats over here. So let's say there is an image over here, you have a bicycle. The same bicycle is repeated over here in the image. Now when you apply the correlation, for example, the result should be same at both these places. So if the result here is X, the result in the other location should also be same. So the operator, it behaves the same everywhere. That is called shift invariant. Shift means to change, move. Invariant means don't care. So we don't care, the operator don't care if we shift the position. If the input is coming from up or down, if the input is same, the output should be the same. Result is same. It does not depend on the location. It only depends on the values. So the value of the output, it depends only on the pattern in the image neighborhood, and it does not depend on the position of the neighborhood. So it does not depend on the value, either it's coming from the top or the bottom of the image. Only it depends on the value. What is the value inside? I hope it's clear. This is called shift invariant. So there are some more properties of convolution. Convolution that we study over here. It has got in total 7 properties. So 2 properties we saw before, they are for linear. So linear has 2 properties, additivity and scaling. One more property for convolution is the shift invariance. So this is 1, 2, 3. And then there are more properties for convolution which you have already studied in your set courses, mathematics, like commutative property. If you have a signal f and g, 2 signals, the convolution between these 2 signals, it does not depend on the order. So f convolve with g is same as g convolve with f, same answer. If the answer is not same, then it's problem. For convolution, it is same. So convolution in this case is same as in addition. If you remember, addition has same property. So this is called commutative property. 3 plus 2 is same as 2 plus 3. Remember? That's why we say that add is commutative. Not all functions are commutative. For example, subtract, is it commutative? No. So 3 minus 2 is not same as 2 minus 3. So add is commutative, but subtract is not commutative. Similarly here, the convolution operator, it is commutative. Clear? Another property is the associativity property. Associative property means that if you have 3 signals, you can write them in any order, the result will be same. F convolve with G, convolve with H, you can change the order in which you process them, it will be the same answer. So again, the same rule applies over here. You can have the values 3 plus 2 plus 4. You can solve them in any order. You can solve it like this, 3 plus 2 plus 4, or you can solve it like this, 3 plus bracket 2 plus 4. Same thing. But this is not always same. In the case of subtraction, it is not possible. So associativity property is also true for multiply. 3 multiply by 2 multiply by 4 is same as if you change how you will process them. You put brackets, you solve any one of them first, no problem. So same case here, convolution is associative. One more property of convolution is that it has got an identity element. Just like in the case of addition. So in the case of addition, the identity element is called as 0. The 0 is the identity element, because if you add 0 to any value, answer is same. So for add, 0 is the identity, but for multiply, 1 is the identity. So for multiply, 1 is identity. For addition, 0 is the identity. So identity is such element that makes no difference on the result, on the input. It makes no difference. So in the case of convolution, the identity element is the one that we studied previously. It's called the impulse signal. Unit impulse, we normally write it like E. So if you have any value, you multiply it with E, the answer will be same value. So if you have F signal, you convolve it, not multiply, the word used, sorry, should use the word convolve. So if you take the signal F, you convolve it with the impulse signal E, the output will be same F signal. And the last property for the convolution is very important. We will be using it in the next chapter. If you take the derivative of the two convolving signals, so let's say you have signals f and g. So when they are convolving, you take the derivative. That derivative is similar if you apply it only to one of the functions. So if you take f and g, the derivative of both of them is same as you apply the derivative. So remember from your mathematics, what is derivative? Derivative gives you the change in the function. So the change in this function with respect to x. So you apply this change finding only on one function. I will extend it. I can write over here, and these two are same as if I apply the derivative on g only. So f convolve with, and here I put the partial derivative of g. So they are same. All these three, they are same. With respect to convolution, they are same. This is an important property of convolution. So all in all, there are 7 properties for convolution. Very important for your exam also. Keep them in mind. Clear? Going next. So here it is, the computational complexity. If you see, we discussed it already. If you have an image which is n by n and the kernel is m by m or w by w, the number of multiplications that you will do will be n square w square. And here you see the operation. So this is 1. It's not visible. It's 1. So in the case of correlation, the output basically is as if you apply the mask. First you rotate it by 180 degrees and then you apply it on the image. Okay. So this is how it is working over here. Separability, leave this slide. So we don't study this. Also here, this one. Going next. So here is a division operator. What you think about it? This I leave it to you. Is the division operator linear? So here you see one example. Division is linear or not? X divided by x plus z is not equal to x by y and x by z. But in the another case, it is equal. So is the division operator, it is linear or not? So linear should have two properties, scaling and additivity. I will leave it to you people, but overall division is not linear. Okay, so division is not linear. Boundary issues we will not study, but remember, if you remember this thing, this is my filter. When I want to apply this filter on the window, so when I apply it on this window, so I take a window and I convolve this, or I correlate this window with this filter. The result that comes, I will put it over here. So like this, I discussed this thing in the last chapter. The whole side rows, the outermost row, one row, on each side, one value will be lost, one cell will be lost, because I don't have anything to take an average for those cells. So these values are shown over here as boundary issues, but we don't study. Just you should know this much, that one value will be lost on each side. How to compensate it, they have given different techniques, but it's not so important. So here is the example. The boundary, one cell is lost. They are just trying to show it larger, but normally one pixel value lost on each side is so small you can't see it. Practically in the lab work you will note that it's not visible, no difference. Okay, so there are some techniques given for this, but we don't study it. All these slides you cancel. So this is also for boundary, so we don't study this also. So keep on going. So here is some practice. This will be in your exam also, in your lab work also. Here is some practice with the filters. This is same question as it was given to your given before. Now what is this signal over here? What do you think? So it is a signal that has 1 in the center, so it is basically impulse. So this was a quiz given before. If you multiply an image, so there is an image over here. So if you not multiply it, sorry, if you correlate an image with the impulse, what will be the output? What will be the answer? The answer will be the original signal, no change at all. Why there is no change? Just try to imagine. You take the value 1 and you take the average. Every place it will give you the same pixel, no change. But if you move this one on the right side, what will happen? So remember, if you previously saw, so we are using the correlation. In the correlation case, the effect will be when you rotate it 180 degrees. So effect will be on this position, on this side. So basically, when you have a 1 on this side, it means that the signal image will be moving to the left side. There will be a black line on the right side. So when there is a 1 on the right side in the impulse signal value is on the right side, the image will be shifted left by 1 pixel. Practically it will not be visible like this, not too much clear. In the lab we will try this. Clear? Now I ask you, let's say if I move, so I put it 0 over here, I move it on this side, what will happen? So it's clear. It will be opposite. There will be a black cells, there will be black pixels over here, and the other side will be, all the image will be shifted to the right side. Okay. Now another question. So if this is 0, if I put 1 over here, what will happen? So exactly, there will be a black row over here of pixels and the whole image will be moved to the downside. That's what I wanted to show you. We will do it, we will try it in the lab work. So here is some practice with the linear filters. You have already done this. This is your original image and the filter used over here is box filter or the averaging filter. So for the box filter, the output will be blur, but noise will be removed, but there is some blurring that will occur. Okay. Now this is another thing. This is very interesting. If what is this thing happening over here? The operation that's happening over here, these two things, what it does is that effectively the result of this minus operation will be minus 0 minus, so remember 1 over 9 is 0.11, so it will be 0 minus 0.11. It will be same for all of them, this, but here it will be 2 minus 0.11. All others will be same. This dash means same. So overall the matrix that is created is, it will be minus 0.11 minus 0.11 repeated everywhere, but here the value will be plus 1.89. Try it yourself, calculate it, and here it will be 0.11 all. So here you see a matrix where all the values are minus, negative, except this value in the center which is very high and positive. This matrix that I create over here, it's called sharpening filter. Sharpening means the edge become very sharp or very pointy. Okay, so over here original image and this image, you will see that this image has the edges very clear. So the difference becomes more clear. Sharpening is the opposite of blurring. So blur, you remember we used it in the last chapter. So opposite of blur, so the blur opposite is sharp. Okay, so this is the sharpening we create. The sharpening filter, we create it like this by subtracting the box filter from this impulse signal. Not impulse, it's a signal which has 2 in the center. Okay, sharpening is an important technique. It's used for example by the police forensics, where they want to analyze some image and they try to enhance the image edges. In the lab work we will see how it works. So this concept is called, this idea over here is called sharpening filter. So one more thing that's interesting that you see over here, that if you change the filter, the result changes a lot. And in the future chapters we will see that we change the filters and we get some very interesting results just by changing filters only. So here is the result of sharpening. What I mean, if this is the original image, the sharpening means it becomes, the edges become more clear. So what are the edges? For example, these wrinkles on the forehead, the coat, the lines on the coat, they become more clear, more visible. So sharpening is the opposite of blurring. Clear? So this is one more important question that we will address in the lab work also. So let's say if you have a filter, its coefficients, they do not add to 1. Okay, so remember I explained this thing in the last chapter very clearly, that if we make a box filter and we divide it by 9. Okay, so if the value of the filter, so in this case overall the average, the sum of all the values is 1. So if you take the sum of this filter, sum will be 1. Now if the sum is not equal to 1, if it is less than 1, then in that case, that mask, when you apply it on some image, it will make the image darker. So if the value of mask is less than 1, it will make the image darker. If the value of the image is greater than 1, it will make the image brighter. So remember, in the image processing we don't want to disturb the image. That's why making the image dark or lighter, it's not good. That's why the filter should always have the value 1. That's why if you remember, I told you that you will divide it by the total number of ones over here. That is the reason for Gaussian filter we divided by 16. Why we divided by 16? Because the total number of values over here, they are 16, so I divide by 16. If I don't divide it by 16, then the matrix, the mask will have the overall value greater than 1. So it will make the image brighter. We will try it ourselves in the lab. Okay, so when you multiply some value greater than 1, so remember from your media computation course, if a pixel value is for example 200, you multiply it with some value greater than 1, it means that you are increasing 200. So overall your image will become more bright. If you multiply 200 with some smaller value, smaller than 1, you will make it dark. Clear? So that's what is happening over here. So what is the quiz? So this is just the idea that I give you. The quiz is different. Quiz says if a filter's coefficients don't add to 1, so means that they are not equal to 1. The sum of these values is not 1. they can be corrected by multiplying by the necessary scale value. Okay, so we can correct it by multiplying the scale value, or the resulting image can be multiplied by the square root of that value after the operation to compensate for the horizontal and vertical application of the filter. So what they want to say is that I have an image I correlated with my filter H, and I get some result I prime. So listen carefully. What they want to say is that this H is not a good, it's a bad filter. Its value is maybe less than 1. Overall, the sum of coefficient is less than 1. So in that case, the output that I get, I prime, it will be maybe darker image, darker than I. So is it possible that I multiply some value over here to make it correct? It should be possible, because remember, the operation that is done over here, it is correlation, and correlation is a linear operation. So if I did some changes over here that are making the image darker, I can multiply those changes on the output also. So that was the second rule, scaling. So let's say I have the image I. If I multiply it with a value 0.8, it will become 0.8i. So I can re-multiply some constant to get my original I value. So what I want to say overall is that the scaling can be used, because scaling is the property of linearity, to get back my original desired output. Because remember, if you multiply a constant on the input side or you multiply a constant on the output side, it is allowed. That is the principle of linearity. Clear? So remember, we discussed previously that there are two types of noises, Gaussian noise, and no, there are three types of noises we discussed. There are many types of noises. We discussed three kinds. It was salt and pepper, impulse noise, and the Gaussian noise. So in general, here you see some of the examples. One of them is Gaussian, you see. So Gaussian is basically adding some random value on the pixels, whereas salt and pepper is basically you add up some dots, black or white dots on the image. Okay. One more thing is the last filter we study over here. So I will come back to this slide. It is called the median filter. Now this is interesting. The idea is more interesting over here. Let's say this is your image. I take one window from the image, only small set of values, just for example. Now in this image, what is the noise? So these are the values that are similar. So all the neighborhood values are same except this value. This is the noise. So it is like the white dot, very bright. Okay. So what this filter does, so it is not a normal filtering. So it is not a filtering that you saw previously in the last chapter. This is called a median filter. So if you remember from your mathematics courses, probability and statistics, median means the value that comes in the middle. So if you take all those values, arrange them, and after arranging, you take the middle value and put the middle value over here. Your noisy value will always be on this side if it's a white dot, or it will be on this side if it's a black dot. So if the value is 0, it will come over here. Or if it's very high, it will come on the other side. So median will always be one of the other values, one of the neighbors that exists, but the noise will not come over here. So you will see in the lab work, we will try with the median. So median filter is a good filter. It does not introduce any new pixel value. No new pixel value is introduced. It is a very good filter to remove black and white dots. We call them spikes. So this filter is very good to remove impulse and both salt and pepper noise. So to remove black and white dots, it's a good filter. And but for Gaussian, it's not so good because Gaussian noise is already an average of the neighborhoods. So this filter, is it linear or not? That is a question. Pause it and think over it. What you think? Is it a linear filter? No, it's not linear. Just like your max operator, max is not linear. Here also it's not linear because the value that you will select over here in the middle, it depends on from where it is coming in the neighbors. So it's not a linear filter. Okay. So median we study over here, and we will do it in the lab work. So the way to remove the noise, till now what we have seen is we saw the assumptions. The way to approach this is, remember that in the last chapter we saw somewhere there were two assumptions we made. One of the assumption is that the image changes smoothly around the pixels. So all the neighbors, they have almost similar values. If the neighborhood changes very rapidly, if the value of the pixel changes very quickly, then how to find the noise? So let's say this example. If there is an image where in practice the value is really changing from 23 to 90. So if the image has so many changes, you cannot find the noise. Not easy. So the changes, they occur smoothly. That is one assumption you make for changing or removing noise. So when we are blurring, what we are doing is basically we replace the pixel value with the average of the neighborhood, local average. And that is fine because the noise is normally modest. It's not too much, and it is a value that is added based on the neighborhood value. But if the neighborhood is changing very quickly, then you can't find the noise. So median filter is another good example where we can use it on these two types of noises very efficiently. Impulse noise, salt and pepper noise. The best filter for these two is median filter. So in the lab work we will see these things in more detail, and we will see practically how it works. So see you then over there. Here is one more example. You see the result. Salt and pepper noise, you see over here lots of dot. When you apply the median filter, it's quite smoother. So here you see the example. All these lines over here, they are the noise. But median filter, when you apply it, all the noises are gone. So median is much better for impulse and salt and pepper noise. So this is the example. This is your input. In this case, this is the noisy signal. So if you apply the median filter, median will take the neighbor values and it will remove this totally. And overall, there is no other change that occurs in the signal. Other values are similar. Whereas if you take the mean or the averaging or the box filter, you will see that it has removed the noise, but it has increased the values elsewhere. So the shape has changed. That's why you see the blur. Blur occurs because the values change everywhere. So that is one of the important thing. The averaging filter causes blur, but median filter never causes blurring. Clear? Median filter, another good property about median filter is that it is edge preserving. Edges are not damaged. You see over here there is an edge. Here the value is high, pixel value. Here the value is low. So when the value of the pixel changes from high to low or low to high, that's an edge. So for example, there is a white line over here and suddenly it becomes black. So this is the boundary or the edge. So median filter is edge preserving. Edges are not disturbed, whereas in the averaging filter, edges are destroyed. That's why you see blurring. So in summary, in chapter 2 and 3 both we saw correlation and convolution in more detail. So previously chapter 2 we saw correlation, and in this chapter we saw the convolution. Remember, correlation is basically flipping the result, whereas convolution gives you the straight image value with blurring effect. Okay, most of the time if your image if your filter is symmetric, then convolution and correlation have no difference, they are same. So what does it mean? If you have a filter like this, all of them are 1. In this case, if you rotate it 180 degrees, result is same, no difference. So for such filters which are symmetric, there is no difference between convolution and correlation. Same as the case for Gaussian filter. If you remember Gaussian filter, that is the reason the Gaussian filter is like this. Now I ask you to rotate it 180 degrees. So if I want to rotate it, this 1 will come over here, then 2, 1, so 2, 1, and then this 2 will come here, and 4 same place, and this 2 will come here, and it is same, no change. So if the filter is symmetric, then convolution is, so for symmetric, the convolution and correlation are same, no difference. Very important concept. Okay. For some other operations in the future, we will see that there is some difference, like for derivatives, convolution and correlation, they don't give the same results. We will see in the next chapter. Remember, overall, filtering is a very important thing because we will use it, and the concepts we understand here in the future, it is very important for our image processing toolbox. So we will now next time go in the lab and we will see all these concepts in more detail to understand these things more clearly.